Hey y'all, we are Memphis University and we're back for another Calculus Done Wrong lesson where we wrong calculus before calculus wrongs us. And today we're going to be concluding our new lessons for our BC integration method unit. What we're going to be talking about is improper integrals. So what makes these integrals improper as opposed to proper? Basically what's going to happen is that they're going to involve infinity somehow. And on the AP exam, usually that infinity will occur in the limits of the integral, usually the upper limit. So for these definite integrals, instead of the ones that we're used to, like from 2 to 3, these integrals will be something like 2 to infinity. But what we're going to see is that while we're going to do this in a very precise way with the letter B, these integrals aren't too bad. You're still going to do the same thing that we've been talking about before. We're going to be taking fundamental theorem of calculus, but instead of plugging in a number, we might be plugging in infinity. This is a nice chance to review some of the BC integrals, so hopefully today we will practice a normal integral without any need for integration methods. Then we might do a USA, we might do parts, we might do partial fractions. So it should be a nice little time here as we review sort of the entire journey of our BC integral career. Keep in mind though that this answers to these questions could be infinity, it could just be a number. It depends on, even if we're finding unbounded area and the area keeps going forever, if the area is getting small and small and small enough, you might not actually have infinite area, you might actually have finite area. So let's see how this works. So the first question again, let's first label this as improper integrals. So improper integrals. So the first question we're going to do is pretty simple. We're going to go from 2, but instead of again to a number, we're going to go to infinity. And we're going to do the integral of 3 over x to the 4th. So a nice little improper integral. Maybe the easiest improper integral that we might see. But it's nice to practice with this. And let's try to write it precisely. So for some reason, it's universally accepted to sort of have a disdain for infinities and the integral, and what we want to do is we want to write it with a limit so that we know exactly what we're talking about. So the way it works is that you're going to write the limit, and for some reason we choose the letter b, but it's the letter b to infinity, and then we have integral 2 to b. And I don't know why this is that much better than this guy right here, but what it's saying is that we're going to find the area from 2 to b, and we're going to let b go all the way to infinity. That's what this says, but it's just written precisely, and this is how everybody does it. So that's how I'm going to write it. So it's going to be 3 over x to the 4th times dx. So once you do this little b action, which again, it's just force biased by standard notation, what you do is you just take the antiderivative. So in this case, for example, what we want to do is the power rule, of course. This is not ln, even if it's a fraction. Remember that any denominator that's not linear is not ln. So what we're going to do is we're going to write it as the power because we're going to use the power rule. So this is going to be the limit as b goes to infinity. One annoying thing that my students find is that you keep to write this limit b infinity, limit b infinity, limit b infinity. I know it's annoying, just write it. So in this case, we're going to do 2 over b. So it's still going from 2 to b, but we're going to rewrite this as 3 times x to the negative 4. Time to do some power rule action. So again, we're going to write limit as b goes to infinity. And so notice this integral, what we're going to do is we're going to add 1 for the power rule. So negative 4 added 1 is negative 3, x to the negative 3. Then you divide by your new exponent, but that's lovely because there's already a 3 here. 3 divided by negative 3 is negative 1. So this is going to be my antiderivative. And then what I'm going to do is I'm going to plug in b, because that's my top thing, and 2. So even if this is a weird sort of guy here, it's not a number, we're going to do the same thing as the fundamental theorem of calculus always dictates us to do, which is we're going to plug in the number top minus bottom. So what we're going to do here is the limit as b goes to infinity. Then we're going to plug in b. Keep in mind that we change things to powers in order to more easily take the antiderivative because that's the power rule. But usually if we want to plug in a number, it's better to change it back to a fraction. Remember that negative x to the negative 3 is the same thing as negative 1 over x cubed. So in this case, it's going to be negative 1 over b cubed. And then it's going to be minus minus. So keep in mind the fundamental theorem of calculus is top minus bottom. So it is minus. So it's going to be minus here, but there's already a negative here. So it's minus minus. So it's going to be plus. And then the 2 is a little bit easier. When we plug into 2 to the negative 3, again, that's 1 over 2 cubed. So that's 1 over 2 cubed, which is going to be 8. you do have to find this limit. Well, notice that when we're going to infinity, you're going to get infinity on the bottom, but hopefully you know that -1 over infinity. If you need to review our limits involving infinity video, this is a good time to do it. But basically, if you have a finite number and your denominator is going to infinity, that fraction is going to be going to 0. For example, if you have one candy bar and you're splitting it up amongst 1 million people, every single person gets such a small piece. And as you have 1 billion people, 1 trillion people, 1 quadrillion people, each person gets a smaller and smaller and smaller piece until it basically goes to 0. So a finite number over infinity, whatever that means, is 0. So notice that in this case, we're just going to get 0 as we take the limit as b goes to infinity. So it looks like our final answer is 1/8. Again, in these questions, you might get finite answers. You might get infinity, depending on what happens when you plug in the limit as b goes to infinity. But keep in mind that this question, again, is pretty simple. We're not doing much, anything new here, really. All we're doing is we're plugging in this infinity at the very end, and that might give us a number or might not. We do have to write it in a very special way, especially on free response questions, because this is what they like to see. So instead of having infinities, because that's considered indecent, I guess, what we're going to do is we're going to write limit as b goes to infinity in every single step, and we'll have the letter b. I don't know why the letter b. But let's keep going. Let's practice again, and let's try to make the integrals a little bit harder, and let's see how this works. So I'm going to erase this. Don't think we need the words improper integrals anymore. So how can you spot an improper integral? Well, the main way is, of course, that there's infinity in the integral. So we're going to do this guy right here, integral. Let's see, what do we want? So I want, I think, x squared here. I want e to the minus x cubed. And again, we do want to involve infinity, so I'm going to put 1 and infinity. So the first thing to do, you see an infinity, let's start writing the b thing, because again, that's how they like us to write it. Even though I never understood exactly the perfect need for that. It seems like a little bit unnecessary, but we're going to placate their desires. So in this case, it's going to be the limit as b goes to infinity, integral of 1 to b, so I'm just changing the infinity to b, so it's a number instead of infinity, x squared e to the minus x cubed times dx. So maybe the most important part of this video, or the most useful part of this video, is just to review all these integration methods. Notice that in this case, we do have a product, so you might think that it's integration by parts, because that's the opposite of the product rule. But notice that this guy's derivative is basically right here, except maybe a constant. So this is actually going to be a u sub, where the u is equal to minus x cubed. So let's do that here. So the u is equal to minus x cubed. That makes the du equal to minus 3x squared times dx. So that's all good. So then we're ready to change our x integral into a u integral. So it's going to be limit as b goes to infinity still. We're going to write an infinity sign. So we chose this u so that we could get e to the u. So that's lovely. E to the u. Then we try to find all of our remaining x's just like normal in a u sub. So it's going to be x squared and dx. So notice that we're doing it correctly because it's in the second line. X squared times dx equals du over -3. As usual, when I replace this, I always like to take out my constants. So in this case, it's going to be du over -3. We'll move the integral a little bit, because again, I like to take out my constant, so I have a -1/3 sitting out here. And then also remember that this is actually a definite u sub. And remember, in the definite u sub, these original numbers were x numbers. I want to change them to be u numbers. And remember how to do that, it's pretty easy. All you do is you take your constants and plug it in. So, for example, for our bottom number, when x is equal to our 1, which was the original bottom number, we're going to plug in 1 here. Looks like we're going to get -1, so that's our new bottom number, -1. Even if this guy has a b, we can do the same thing. When x is equal to b, what's our new top number? Well, it looks like it's going to be -b cubed. So x is equal to -b cubed. Again, even if it's a weird b thing, it's still the same idea. Change your x numbers to u numbers, even if it includes a b. So in this case, it's going to be -b cubed. Remember that in a u sub, you don't have to remember any more x's. We don't have to look at any of this work yet. because we changed everything to be in terms of u, so I'm only going to be focusing on this. I change all my x's to u in the integrand, and I also change all my x's to u in the numbers. So again, all I have to think about are u's now. So what's the antiderivative here? Well, it's the best antiderivative in the world. What's the antiderivative of e to the u? Well, that's just, of course, is just e to the u. So it looks like we still have our limit in the front, and we're going to have negative 1/3 e to the u. And then, of course, again, we are going to focus on u's. So now it's fundamental theorem of calculus time, really just a pure party. So what we're going to do is we're going to take the top thing, plug it in, minus the bottom thing, just like normal. So it's going to be the limit as b goes to infinity. When we plug in negative b cubed, it'll be negative 1/3 e to the negative b cubed. Then when we plug in negative 1, it'll be minus minus. So again, it's fundamental theorem of calculus, top minus bottom. But oftentimes you might have negatives in the antiderivative, which is the case here. So we have a negative inside the antiderivative. So it'll be plus 1/3 e to the negative 1. So keep in mind that we are going to plug in infinity. This is again in our limits involving infinity video, which occurred a long time ago if you're watching these successively, because those were back then when we were doing limits. But keep in mind that when you have e to the negative infinity, again, this is with limits. What I like to do is I like to evaluate this slowly. This is the same thing as 1 over e to the infinity. What's 1 over e to the infinity? Because that was a negative exponent. Well, e to the infinity is e times e times e times e, just an infinite number of times. So that's going to be 1 over infinity, which again is going to be 0 from that candy bar argument. So when I plug in infinity here, notice it will be infinity cubed, which is infinity, but then it'll be minus infinity, and e to the minus infinity. We sort of wrote this with bad notation. We didn't write it with limits, but it's probably easier to understand. E to the negative infinity is 0. So when we plug in infinity, this term goes away. This term didn't have a b, so this is actually our final answer, 1 over 3e. So again, all of this improper integrals business, these infinity business, the b's and things like that, it doesn't really change the question too much. We still did our u sub here. We still changed the x numbers to u numbers, even if it involves b's. And then we just plugged in top minus bottom into the antiderivative. And what we saw is that this term right here went to 0, and we did not complain, of course. And then finally, what was our final answer? 1 over 3e. So let's do some more questions, because that's what we're here for. So this is a nice little u sub. We're going to do a nice parts now. So I'm going to erase this. I'm going to erase, and let's finish erasing. So my next question is going to be find the area. So find the area, the unbounded area. So sometimes they don't actually present the integral for you. Sometimes you have to interpret it, but it's find the unbounded area under f of x, and this is going to be our function, so this is the key thing, x e to the negative 3x. And it's from bounded by on the left, so bounded on the left, by the function, or by the vertical line x is equal to 2. So basically, what we have here, don't know exactly what this graph looks like, but you have the line x is equal to 2. You have this graph, which I believe looks like something like this. And this will never touch the sky, and what we're going to do is we're trying to find this area right here. This might not be the perfect graph, so I'm going to erase it just in case it's not the graph. But hopefully you see that it is bounded on the left by a side, so this sort of defines the function. And then over here, it's getting closer and closer to the x-axis. But notice it will never touch. So this is sort of the miracle of improper integrals. We might have an area that keeps on going forever, but because it's so close to the x-axis, we might actually get a finite number for our area. So let's see that in action. So what we're going to do is we're just going to do the integral. Because the left side was 2, that's the bottom number. And then again, we're going to infinity. And now we're going to do this integral right here. X e to the minus 3x. So hopefully you see the difference between this question and the previous question. Again, it's a nice review of u subs versus integration by parts. Here, the exponent's derivative is not this, because it's the same sort of power. They're both x to the 1s. So in this case, this will be integration by parts. So what's our little formula here, which of course u du v dv. Again, even if we have this infinity business, we can still do our normal integration by parts method. We can use Lyautey. So remember, Lyautey stands for logarithmic, inverse trig, algebraic trig, and exponential. And what it allows us to do is to choose one of these guys to be u, one of these guys to be dv. So x is algebraic, e is exponential, as its name might imply. So what we're going to do is we're going to put the e to the negative 3x in this slot right here. Then we're going to put the x in this slot right here. We're going to take the derivative of x, so that's just going to be dx. We're going to take the integral of e to the minus 3x. These are some of the hardest integration by parts questions on the AP exam. It is e to something, e to minus 3x. But this is technically a u sub as I take this integral because there's a minus 3x here. So just like with the chain rule, it's e to the minus 3x times negative 3. When you want to skip an easy u sub, what you do is instead of multiplying by the derivative of the inside function, you multiply by the reciprocal of the derivative of the inside function. So instead of multiplying by negative 3, which is what I would do with the derivative, I'm actually going to multiply by negative 1/3. And you can check that the derivative of this v is e to the minus 3x. So again, oftentimes when you have these e to the 3x's, maybe sine of 3x, cosine of 3x, it's often easier just to skip the u sub. You certainly can do it if you feel the need. U is equal to 3x, du is equal to 3dx, and so on. But I think it's easier just to skip it or just take the antiderivative. Boom. So now that we have this little rectangle, we can go for the answer. So what we're going to do is we're going to write equal here. So first off, remember it's u times v, so it's going to be negative 1/3 x times e to the minus 3x. And what we're going to do is we're going to plug infinity in 2. But for right now, I think it will be easier just to find this integral and then just plug in infinity in 2 into the last answer. So I'm going to leave the top minus bottom for now. Remember that in integration by parts with a definite integral, you can do top minus bottom into the uv, then take the antiderivative and do top minus bottom and add all the answers. Or what you can do is find the final antiderivative and then do top minus bottom. And I feel like that's a little bit easier in this case. So that's what I'm going to do here. So it's going to be u times v minus the integral of v du. So it's e to the minus 3x times dx. Just like normal, if I have a constant, I could write negative 1/3 here, but I'm going to take it out. So it's going to be plus 1/3. And it will still have the same numbers. It will be going from 2 to infinity. 2 to infinity. We didn't write it with the b's, so let's actually write it with the b's. So this is going to be b here. We're going to write the limit as b goes to infinity over here. And then here we're going to plug in b again and 2. But just keep in mind that we decided that we're going to take the antiderivative and then we'll plug in top minus bottom. So I feel like, because then we can plug in infinity one less time and it should be easier. So in this case, we're going to get limit as b goes to infinity. Still this guy right here, negative 1/3 x times e to the minus 3x. So all we have to do now is take the antiderivative of e to the minus 3x, but that's the same thing we just did. Keep in mind that there's another negative 1/3 because we're taking another antiderivative. So in this case, it's going to be still e to the minus 3x, but it'll be times negative 1/3 because of that skipping the u sub step, that reverse chain rule. So it'll be times negative 1/3, but there's already a 1/3 in front of the integral, and 1/3 times 1/3 is 1/9. See how everything is going? So in this case, it's going to be negative 1/9. And then now let's plug in top minus bottom. So in this case, it's going to be b and our bottom number, which is 2. So this is going to be a little bit tricky. So the first one we're going to plug in is b into all of this, and then we're going to plug in 2 into all of this. And let's see what happens. So it's the limit as b goes to infinity. Let's try to write things as fractions because, again, usually when you have fractions, it's easier to understand these negative exponents. So it's going to be negative 1/3. When you plug in b, it'll be b over e to the minus, e to the 3b, because we're writing this as a fraction. Then we're plugging in b here, so it's going to be minus 1/9 e to the negative 3b, which is the same thing as 1 over e to the 3b again. So all I'm doing is fundamental theorem of calculus, top minus bottom, where the top thing was plugging in b, so all these x's became b's, and I wrote it as fractions as opposed to negative exponents. So this is the top. The bottom is going to be easier because it's just the number 2, and I understand 2 better than I understand b. So it's going to be negative 2/3. Looks like it's going to be e to the negative 6 because 2 times negative 3 is 6. So it's e to the negative 6 minus 1/9 e to the negative 6 at the end. Well, we might as well simplify this while we have a chance. So it's going to be negative 2/3, so that's negative 6/9, sorry, 2/3 of course is 6/9. So it looks like we have negative 6/9 minus 1/9, that's negative 7/9. There's a negative in front, so this is all going to be 7/9 over e to the negative 6. So that's all of this stuff, the minus bottom. Let's try to do this top now. So the top is a little bit confusing. So notice that we're going to plug in infinity here. So when we plug in infinity here, it's going to be 1 over e to the infinity. Remember that e to the infinity is infinity. So we have that 1 over infinity business again. That often happens when you have improper integrals. So this term is going to go to 0 when you plug in infinity. What about this guy right here? Well, when you take this guy right here, what you're going to get is you're going to get infinity because you're going to plug in b, infinity for b. You're also going to get infinity on the bottom because again, e to the infinity is infinity. So when I plug in infinity, again, it's going to be infinity over infinity. There's various ways to do this. I think the easiest way is to L'Hopital this, where we're taking the derivative with respect to b. So we can do that on the side here. We're going to do negative 1/3 b over e to the b, e to the 3b really. So I'm just going to L'Hopital this real quick. Just this term, when I take the limit as b goes to infinity, again, I get infinity over infinity. So I can apply L'Hopital's rule, a nice reveal of L'Hopital's rule. Don't confuse it with quotient rule. The derivative of the top, the derivative of the bottom, and then redo the limit. So in this case, it's going to be negative 1, because that's the derivative of the top. The derivative of b is 1. And then what's the derivative of e to the 3b? Well, that's going to be 9 e to the 3b. Because what's the derivative of e to the 3b? That's 3 e to the 3b. There's already a 3 there, so it's going to be 9 e to the 3b. We're going to plug in infinity still, because we're taking the derivative with respect to b in this case. And when we plug in infinity, notice that we still get this action of e to the infinity on the denominator. 1 over that is going to be 0. So actually, all of this will be 0. So you're actually left with this guy right here. Top minus bottom, where the answer ended up being just minus bottom, which was negative. So that's why the final answer is 7/9 e to the negative 6. So this was quite complicated, but hopefully you see that it's the same thing as normal integration by parts. We notice that it's integration by parts. We decide which one we want for u, dv. We take the derivative of u, we take the integral of dv, keeping in mind that we might need to skip a u sub or do a u sub as we go from dv to v. Then we do our nice little formula. What's this integral? What's the integral of u times v? So it's u times v minus the integral of v du. We took out our negative 1/3, so it became plus 1/3. We could have done top minus bottom into this guy right here and then take the antiderivative to do top minus bottom. But what we decided is just to take the final antiderivative and then do top minus bottom, which is perfectly allowed. This integral e to the minus 3x still required a u sub, so that's why it became negative 1/9 e to the minus 3x because another negative 1/3 is coming out. We plugged in top minus bottom. The 2 was certainly pretty easy, but even the b was also not that bad. When we plugged in the b into the top minus bottom, what happened was nothing too crazy. Maybe it was a little bit crazy, but when we plugged in b here, this term became 0 because it was 1 over infinity, and this term we showed was 0 as well using L'Hopital's rule. So quite an involved process, but hopefully you see that the main issue of this was not the actual infinities itself. It was just implying an integration by parts question, which usually involves a lot of steps. And so that's that. Let's do the other BC integral that can appear on the free response questions. Let's do integration by partial fractions, maybe my favorite integration method for BC. So let me erase this. Hopefully you can see that the work was quite long. We did appreciate the miracle of life where the integral of this function, again, even if it's unbounded, the area between 2 and basically forever is still the finite number 7 over 9 e to the negative 6. But let's do a partial fraction one. So I'm going to erase this. I'm going to erase, finishing erasing. So let's do this. My board is a little bit dirty and smudgy, but hopefully you can forgive that. Let's do this integration by partial fractions. So in this case, what I'm going to do is I'm going to do the integral of 7, let's do infinity, and let's do 12 over x squared minus 9 times dx. So hopefully, if you look at this integral, first off, it is improper because it has a nice little infinity in the top. But hopefully you can recognize that this is, in fact, a partial fraction question. If there were an x here, then it would suddenly become a u sub because the derivative of the denominator would be in the question. But this is a nice classic partial fractions. So let's review partial fractions. First off, remember that when we have partial fractions with numbers on top and bottom, even if this one is infinity, what we're going to do is we're just going to find the partial fraction process, and at the very end, after we take the antiderivative, it will involve ln's, then we'll do top minus bottom. There's no need to change the numbers or anything like that, and the use of, so let's just try the partial fraction process. So in this case, what it's going to be is going to be the integral. We can do the b thing, because that's what they want us to do. 7 to b, little b. Hopefully you won't confuse little b with big B because there's a big B in the partial fraction, there's a little b in the improper, but everything's going to be okay. So it's going to be a over this factor. Remember, x squared minus 9, of course, is x minus 3 times x plus 3. So it's over the factored forms. So let's leave calculus aside and let's do a little bit of algebra to make this a legal partial fraction decomposition. So remember what you do is you cross multiply. A times x plus 3 plus b times x minus 3. You set this equal to the original numerator, which in this case is 12. I'm going to distribute real quick. Ax plus 3a plus 3bx, not 3b, but bx minus 3b. So I'm just distributing this b into this a into this, just to have a little bit of fun, equals 12. So then what I need to do is I need to form my x equation and my not x equation. But this one's not going to be too bad. Ax plus bx is equal to 0x. So I have the nice equation a plus b equals 0. Then I have the equation, the not x equation. It's going to be 3a minus 3b equals 12. So it's going to be 3a minus 3b. That's going to equal 12. So let's just solve this system of equations. Looks like I can divide everything by 3 here. A minus b is equal to, let's see, what do we have here? 4, because 12 divided by 3 is 4. Don't know why it took me so much time, but sometimes your calculator really isn't working in your mind. But let's move on. A is equal to negative b. Looks like the easiest thing to do in this case. You can eliminate, of course, you can substitute. But in this case, it looks like substitution is easier. But again, the actual equations themselves is more important. How you do it is you have an x equation, ax plus bx is equal to 0, so a plus b equals 0, 3a minus 3b equals 12. The not x equation, system of equation time. So in this case, we're going to use substitution. So it's going to be minus b is equal to 4. So it looks like b is equal to minus 2, because it will be minus 2b equals 4, so b is minus 2. That makes a equal to 2, because it's negative. So let's go for the question. So I'm going to be lazy here, but let's actually not be lazy for once. Let's write the limit as b goes to infinity. And again, we're splitting this up into two integrals. 7 over b, and then we're going to do 7 and b as well. Little b. So just like normal, I take the 2 that I just solved, so nice and innocent, I guess. We're going to take this, plug it in right here. So it's going to be 2 over x minus 3. But again, I like to take out my constant. So instead of writing 2 over x minus 3, I'm going to write x minus 3 in the integrand here with a dx. But instead, I'm going to take the 2 out. Same thing here. I have a negative 2. I could put it right here, but I'm going to take it out. So it's going to become minus 2, and then it'll be the integral of 1 over x plus 3. We can erase this dx to save a little space and write it over here. So now it's time for antiderivative time. Hopefully you remember that for partial fractions, what it is always ln. So in this case, it's going to be 2 ln of x minus 3. We still have the b thing. So b to infinity, it will be 2 ln of x minus 3 minus 2 ln of x plus 3. And what we're going to do is we're going to plug in b and 7. So b and 7. One thing we do, especially when we have these infinities, I've seen this appear a few times on the AP exam when we have these infinities with partial fractions. When you have a number times ln with the same number times ln with a minus, remember that becomes a single ln. Subtraction ln is the same thing as division of a single ln. So in this case, what it's going to be the limit, sort of running out of space here, but I think we can finish. It'll be the limit as bn of 2 ln of a single absolute value, this one over this one. And we're still plugging in bn and 7. So hopefully you can tell that these are absolute value, this is a vertical bar. All of this is quite confusing. But again, all we're doing is we're just taking our answer and we're doing a very standard ln property, which is that the ln of something minus the ln of something is the ln of the numerator divided by the denominator. So the ln of this minus the ln of this is the ln of x minus 3 over x plus 3. So let's see what happens. Well, when you plug in b goes to infinity, we do have to do top minus bottom. But notice that when we plug in infinity, we can take the infinity into the absolute value, into the ln, because ln is continuous towards the infinity side. And just keep in mind that we have a same heavy thing. Basically, what's the limit as b goes to infinity of just this thing right here? That's going to be 1 because it's same heavy inside. The leading exponents are the same, so it's going to be 1 over 1. The ratio, remember that if you have something same heavy, the answer is the ratio of the leading coefficients of the numerator and the denominator. So in this case, it's going to be 1. So I'm going to write the answer right here, which is very unorganized, but hopefully you can forgive me. When I plug in b, again, you'll have, when you plug in the infinities here, when you take the limit inside the ln's, you're going to get 2 ln of 1. Then when you plug in 7, well, 7 is a standard number, so when you plug in 7, it'll be 2 ln of 7 minus 3, that's 4 over 10. 7 minus 3, 7 plus 3. Keep in mind though that 2 ln of 1 is 0. So our final answer, if you don't want to simplify anymore, is just going to be negative 2 ln of 4 tenths. And that's all it is. So again, the main thing about this, in my opinion, was just doing this process, doing the integration by partial fraction process. And at the very end, the only thing new in this video was that instead of plugging in 2 finite numbers, we plugged in infinity. How did we plug in infinity? We found the limit as b approached infinity. In this case, it made the ln of 1, which is 0. But hopefully you see that the partial fraction process didn't change at all. We broke it up. We formed an x equation and a non-x equation. We did a nice little system of equations, and we found our answers. And that's what it was. So that's how you do improper integrals. When you have that infinity on the top, what you want to do is you want to write the limit as b goes to infinity. Let me show you one more thing, which is very, very tricky. It's some of the trickiest questions on the AP exam, just real quick. So I'm going to erase this. I'm going to erase this now. I'm going to erase this. And let's do one integral that seems like it's really easy, and it doesn't look like it has any infinities, but it is, by definition, an improper integral. And let's see why. So I'm going to do the integral from negative 1 to 2 of just 1 over x to the cubed. So this is going to be my integral, and it seems like this shouldn't be in this video because there's no infinity in the top, just like all the previous ones. But this is one of the most tricky questions that are on the AP exam. Basically, you have to treat this integral very, very carefully because the interval that it is integrated on goes through where the bottom makes it 0. Basically, we're integrating over a vertical asymptote. So notice that when we plug in, let's do x to the 4th actually. But it will work with x to the cube, but let's do x to the 4th. So keep in mind that when we plug in 0, 0 makes the bottom non-existent. So we're integrating over a vertical asymptote. So in order to do that, what you need to do is you need to be careful when you integrate over a vertical asymptote. So what you have to do is you have to split it up at the vertical asymptote. So in this case, what it's going to be is it's going to be this integral, the integral from negative 1 to, now we're going to write b. b isn't going to be 0 now, b is going to be the vertical asymptote, which is x equals 0. So it's going to be limit as b goes to 0 from the left, because it's going to be negative 1 to this b number of 1 over x to the 4th. Then we're going to integrate the limit as b goes from 0 to the right. And what's going to happen is we're going to have, we're going to go from this number to 2. So it's going to be our small, middle, big rule for the integral properties. When you integrate from negative 1 to a middle number to a final number, that's the same thing as integrating from negative 1 to 2. But again, we're breaking this up because at x is equal to 0, 1 over x to the fourth doesn't exist. We are integrating over a vertical asymptote, so we might be integrating infinite area because as it goes to the vertical asymptote, we might have infinite area. So let's see what happens here. Just like the very first one we did in this video, we want to write this as an exponent, so it's going to be x to the negative 4. And what's going to happen is we're going to just take this integral. So I'm just taking this integral first, and I might do this integral. You'll see why I don't do it later on. So what we do is we're going to add 1, so it's going to be x to the negative 3 with a negative in front. Remember that you divide by your new exponent, so it's going to be negative 1/3 in fact. And what we're going to do is we're going to plug in b and negative 1. Limit, still as b goes to negative 0 from the left. Again, it's not infinity, it's 0 to the left. This is an improper integral. They don't call it infinity integrals, they call it improper integrals because whenever something might arise, in this case, the problem is that 0 makes this a vertical asymptote. So we're still going to do top minus bottom. Notice that when we plug in here, it'll be the limit as b goes to 0 minus negative 1 over 3b to the third. Again, I'm writing this as a fraction. The other part is not that bad. It's going to be minus minus plus 1/3 of negative 1 to the negative 3, which is the same thing as 1 over negative 1 cubed. But this is going to be the problem term. Notice that when we plug in 0 here, as the limit of b goes to 0 from the left, what we're going to do is this term is actually going to be does not exist. Because what's going to happen is you're going to basically divide by 0, and of course you're not allowed to divide by 0. So this entire integral doesn't exist. So we don't even need to find the second integral, because if you add does not exist to something, well, all of it is does not exist. So basically this question, as might arise in improper integrals, the answer is does not exist. So again, this is very, very tricky to spot. Because if you took this integral sort of blindly without knowing improper integrals, you would spit out an answer, but unfortunately the answer is wrong. You would write x to the negative 4, you would add 1 and flip, you would plug in top minus bottom, and you would just get some fraction. But why is that fraction wrong? It's because of this does not exist, because you're integrating over the vertical asymptote. Again, these are very, very hard to spot. If I'm doing a bunch of integrals, as I like to do for fun, I might skip over this integral and I might just do it regularly. How can you tell if this is a weird integral? Well, usually there's a lot of wording and hints. Usually this is a multiple choice answer where some of the multiple choice answers are like, well, this integral doesn't exist because of a certain reason. And again, what is the certain reason? Well, you can't evaluate the antiderivative at the point that is the problem point, which is why this function is integral doesn't exist. What you need to do is you don't need to focus on this too much. Just be aware that this situation does arise. Whenever you're integrating over the vertical asymptote, you might get something that doesn't exist. Perhaps you wouldn't, but in this case, we do get something that doesn't exist, which is why we had to do all this work. We had to split up this integral to make sure that in this case, they did not exist. But the more important questions, the ones that are more relevant to the BC exams, the ones that appear every single year, potentially even in the free response questions, were those questions that we started off with in the beginning, just having integrals with infinity, where we just do u subs or integration by parts or partial fractions the same way as normal, except plugging in infinity instead of a number. If you want more practice with this, because this concludes our video, what you should do is check out our Girls Teach Calculus video. It's in the description below, where one of my former students practices several of these examples. She does some that are very basic, like just the power rule. She does some involving u subs and some involving parts. And at the very end of the video, she does some of these questions as well. Questions that are a little bit trickier to spot, where you do have to split it up at the problem point or over the vertical asymptote. But hopefully this video was beneficial for you. I feel like I had a fun time because I was able to review various integration methods with you, u subs, parts, partial fractions. Keep in mind that if you want more review, that's going to be our next Calculus Done Wrong video, where we are going to review all of our BC integrals sort of as a group. And we're really going to focus on when to do what, because that's oftentimes students' biggest issues. Not, here's an integration by parts question, now do the integration by parts process, or here's a partial fraction question, do a partial fraction. It's here's 10 integrals, which one, what method do you use for which one? So that's what we're going to try to talk about in that video. And again, we're going to try to review sort of all of our integration methods that could appear on the BC version of the AP exam. So until then, thanks again for watching just like normal, and I hope to see you then. Thanks again.